Hi everyone, this talk is going to be a compiler talk about the C2 compiler in OpenJDK, specifically a new optimization that we worked on, Microsoft surprisingly, but so called stack allocation. In this particular talk, I'll start with a quick introduction what currently exists in HOSPA C2, extend with the work we did in our engineering group, then show some results on popular benchmarks, and hopefully kind of finish off with the stuff we still need to do. So it's still very much a work in progress. We haven't submitted a patch to the OpenJDK mailing list, compiler list. But it's just a warning. I mean, maybe boring for a bunch of people. This is going to be a bunch of compiler jargon here. I can't work around that, fortunately. So stack allocation. So the main motivation was to alleviate some of the GC pressure. It was originally brought to us, we started working on this by Kirk Pepperdine. Some of you may know him. He's big on GC tuning in the Java world, and he often would say, as we were looking at some Spark workloads to improve them, and say, oh, these allocations in Scala give the GC seizures and so on, so it's really bad. You guys should try to fix this. So, so how we actually going to try doing this is by saying we're going to eliminate the location, but not quite. We're going to allocate on the stack frame rather than on the heap. It's a known optimization compiler. It's just somewhat not actually being done in C2 yet. So, so when can we do this is when we say the object does not escape the current method context, and typically objects escape with returns, calls to methods, or maybe stored into fields, passed around. So there are places where we can do it, places where we can't. So here's an example. We have a very simple Java program here with 3 allocations. We got box 2 integers, and then we finally return another one. Integer is immutable class, so there's 2 additions, create a new object, and that's popped and returned. So the first 2 objects do not escape the method, but the last one does. And the way that we do tell which ones do escape, which ones don't, is by this compiler backend pass called escape analysis. So a bit more about escape analysis. Now, escape analysis was introduced by this paper. It was introduced by IBM TJ Watson Research a while back, and essentially they had in the paper 2 different kind of optimizations described, flow sensitive one and flow insensitive. The one that's implemented in C2 is the flow insensitive version of it, and is the right choice actually. The paper describes both of them, but it actually shows that they do similarly well, and the flow insensitive is much easier to implement, maintain, and less memory intensive. Currently it's used in C2 for the following 2 purposes. So we use it for monitor elimination, which means if the objects are proven that they're not escaping, therefore they can only be seen by one thread. So we can eliminate the monitor enter and monitor exit operations on these objects. So no synchronization on them. So say you're using a string buffer instead of string builder, well, this will help. The second one, which was interesting for us, it was the scalar replacement. So this is the form of an optimization that we kind of extended. So scalar replacement goes by the same sort of concept. You take out the original object, you break it apart into the individual parts, so you actually make away the actual allocation. So the breaking up of the object turns it into a normal autos or local variables that sit on the stack. Therefore, no heap allocation there. Okay, so here is another example, slightly different than before, but maybe you'll notice subtle difference, people that know this stuff, but we are doing the 3 allocation as before. Now let's move on to the next step, and the scalar replacement will come in and actually turn it into this. This is what the final program would actually behave like. The integer field within the integer object, the primitive data type, was extracted and actually stored as a local variable on the stack. Now, when can we do this? Mainly when we actually don't need the original form of the object anymore. So when we can actually prove that the object as a whole integer is not needed. Now, let's see some of the limitations with scalar replacement. So when we looked at the code, there's a number of reasons why scalar replacement can't fail. But when we did the analysis and ran a bunch of benchmarks and workloads to see what was the main cause of scalar replacement failing in COSPOT C2, is introduction of control flow. So namely, this is compiler talk again, like phi over here. We have the two definitions on two sides of the control flow. One is the object being instantiated, this new class object here, my class. On the other side, we're pulling it out of an array. Now coming down to the last return object.x, now which one do we have in our hands? Therefore, we need the original shape of the object. We need to do a field load of that object. Because on one side, maybe scalarly placed, but the other side will need a full bloody object coming from that array. So how common is this issue? So I'm back to my original example. So the side that we have on the left here, we can scalarly replace that. But that's not what typically happens with auto-boxing. The side on the right, C2 is unable to handle. Mainly because integer value off, which is what actually happens when you auto-box a primitive data type, internally has the exact same pattern I showed on the previous slide. It has a compare actually with two ranges, minus 128 to 127, which is also configurable. If the values fall in this range, you're getting a pre-cached integer object from a static array, which is a poor man's version of elimination of allocations. But it does actually work for that range of objects. But every time you go above that range or beneath that range, you get a actually heap allocated object. So can we make this work? So there's compiler optimizations that could potentially make this little example here work. However, it has some drawbacks. One typical way we could do this is by actually cloning. Optimizations in the backend optimizations could potentially say, well, we have a condition, we go either way, so why don't we just specialize the method body for this side and for that side. But let's say you have another branch, then it gets unwild. It becomes exponential, so code grows insanely, so it's not actually very useful. Other ways you can do that is maybe by code motion, but then you're stuck with side effects. Let's say the array we're pulling out, that object, this object was a null object. So can you actually, what if you had to throw the null point exception? It won't be on the wrong line. So these kind of optimizations do have limitations in how actually often can we apply them. Now, this is what we actually came up with. Said, well, we don't actually have to scale replace it. What if we actually allocate it, but actually allocate it on the stack? So the object shape is preserved as it typically was, and it just lives on the stack just like the primitive, which is a little bit of extra stuff. It has flags field, it has a class pointer, everything you normally would expect from an object. Now, is this useful? Well, yeah, let's consider this example. Like you have this loop over here. I mean, I cleverly returned the primitive data type so my object doesn't escape, but if this was the case here, this loop will keep generating new objects every time around. Integer is immutable, therefore, new object for every new addition you do. So, stack allocation. Will it work on previous example? Yeah, because on both sides, now we actually have a plain on Java object. So the object.x field load, the get field that happens there, has no problem existing. From one side, it will read from the stack. On the other side, it will read from the object it got from the static array. Okay, so how do we implement this in C2? Come to the second part of the presentation. So Charlie Gracie and myself, inspired by the words of Kirk, started looking into implementing this with stack allocation. We had to modify escape analysis in C2 to recognize cases where we can safely stack allocate the object. Not all non-escaping objects can be stack allocated. I'll show some of the limitations later on, but there's plenty of them. We implemented the stack allocation path in macro expansion, so we had to actually write a separate path that took out everything else. We removed everything else but the path where we stack allocate the object. So how do we stack allocate? And this was one of the big revelations. We actually used box lock node, which was used for monitors, because mainly we needed a way to communicate stack oop, which was not done in any other way, from the IR back to the code generator to say, hey, this should be a pointer reference on the stack somewhere. So right now, our stack allocate objects end up where the lock slots would be, which is right after all the spills and locals before the preserve registers on the frame. So, so other stuff we had to actually worry about. And as soon as we did that, we got immediately asserts in the garbage collector, said, what the hell is this? You're giving me an OOP reference on the stack? That's not right. So we had to actually extend GC root scanning to support these objects. Because what it'll look like, there will be a local on the stack that points to another stack location, which didn't quite sit right. A more kind of subtle issue I'll describe later is detecting live ranges of objects in loops. And the other two items, removing the right barriers, we obviously can't do them because you do a card mark on a stack location, it's not good. And then the other two were already being done, similar code we found for scalar replacement. So we were able to leverage that. We had to kind of similarly implement heapification objects on de-optimization. So any safe point that the allocation can reach, we had to inject this scalar replace alloc node, I believe it was called, where we describe which fields need to be copied over to a heap object. So here's the GC root scanning. Typically, what you normally see is now below the locals, you have a pure stack allocated objects. The first 5 over here will be a flags field, then we have the class pointer and some reference. So the GC need to be thought that, well, as you're walking the stack, you have a reference coming over here. You need to find all the OOP fields and actually mark them so you don't actually lose any objects. Now this overlapping live ranges was kind of like a subtle gotcha. And to be honest, I kind of knew this, but I forgot about it. I used to work in IBM on the Testarossa OpenJ9 compiler, and we used to do this, but sort of had to relearn it from scratch. It's an interesting case where if these two objects as we have them here, let's say, are stack allocated, as soon as we get into the definition, which is definition V2, where value equals result, what ends up happening is that these two addresses, which are actually addresses on the stack, become the same. So what that definition is, coming back on the second iteration of the loop, well, it'll be the address that result was before. But result is stack allocated, it's always the same address. So now all of a sudden what you end up doing is, well, after you first enter this if, you never enter it again. So typically when this was a heap allocation, you will get a new address every time. You allocate from the thread local heap buffer, or you allocate from the heap somewhere, but it's a new address. So your address comparison will work, and the location on where the object is stored is different. But once it's on the stack, it's always the same, which we want to do. We want to actually reuse this for the purpose of better cache, page misses, and also remove the allocation. Well, we end up in this problem. So we had to add code to detect this and actually reject one of them as a candidate for stack allocation. One of them heap, the other one stack, is fine. So we go into the current limitations. So we have a few limitations we can actually do right now. We don't stack allocate object with monitors. It's kind of a side effect with box lock node. We just didn't finish the work. It's not hard to do. But some of the monitor elimination code eventually compacts our box lock slots for stack allocate objects, so we mess up. We don't, but this is the second one is the main issue that we have with performance right now. We do not allow stack allocate objects to be pointed to each other. So obviously a heap parent would mean escaping, so that's actually handled by escape analysis, but stack allocate to stack allocate is not allowed at the moment. There's ways to resolve that, but right now we don't do it. We don't have compressed OOPs support yet. And this is mainly because you can have a merge point, one side a heap object, the other side a stack allocate object. It goes through an encode P, gets stored as a compressed in the stack. Well, compressing a stack doesn't work because you cannot guarantee that the address range will be within that 32-bit space. We don't stack allocate arrays at the moment as well. We just ran out of time. There's no particular reason why we didn't do it. Primitive arrays would be simple. Reference array, special consideration with array copies, so we just didn't have time to finish this presentation and come here and talk about this. And finally, thank you, Ron Pressler. We actually may need to do something special for Project Loom here. Either prevent stack allocation of objects that live across method calls, because in the mode where they do the fast relocation of the stack, it's just a simple mem copy. So if you have a reference on the stack pointing to a stack object, well, nobody's there to patch it, to update that. So we'll get there eventually. So now some good news, actually. So these are the performance improvements that we actually got with this prototype that we have. Being a compiler guy, for me, this is amazing, because I usually would work for 3-4 months for 2% or 3% improvement. And having a range of applications actually get significant speed ups is actually quite good to see. One of the stack allocation to stack allocated object would be another massive improvements if we get it right, because there's certain patterns in Scala that are very common that do have an object graph pointing to each other, which we currently reject. And so finally, the last bit of the presentation. So when and where can we see this patch? Well, nowhere right now. So Charlie and I are in the process of migrating our patch from JDK 11. There's no particular reason why I picked JDK 11. Just we were looking at Spark, sort of continued down that path from the build we're using. We're migrating to tip, cleaning up the code. And as soon as it's done, we'll actually post this to the compiler dev mailing list and ask for review. That's the plan. So our next steps from our perspective are that we have to stabilize the prototype and clean it up. We still have a few crashes. We haven't looked at every of those methods or benchmarks we couldn't run because there were issues. Started working on removing the limitations one by one. Stack allocated would be probably my first pick. Right now, we only support G1 and PGC with a heap with a mark extension to walk stack allocated objects. So we need to extend and see how it actually works in other GC modes like Shenandoah, ZGC, and finally look for more opportunities in other real-world applications. I want to see if we can actually improve, the various REST frameworks that are out there that people build with, and maybe Elasticsearch products like that. And which leads me to the end of the presentation here, which is, if you liked what you saw here, please stay in touch. We'd like to actually work with everyone here. Both Charlie and I are really new to the code base and need a lot of help to actually make this a reality. And helping us review the patch would be awesome if anybody is willing to do that. That's it. Thank you. Any questions? Do we have time?
Yes, we do.
5 minutes.
Are you all completely stunned by that? Oh, not everybody, evidently.
Yeah.
So the question is, can you say something about your write barrier implementation? You said that it's always a performance win, but if the stack allocation fails, then presumably you've got a more expensive write barrier now?
That's right. So we currently, and that's exactly the where I was going. I have actually 2 appendix slides, which I'm actually going to talk about the reference-to-reference issues, which leads me to the stack write barrier. So we currently remove the write barriers on stack allocated objects because we are sure that when we make it a candidate for stack allocation, there will be never it be coming a part of something else. So if you store a field if it has a field and you write into that field, you don't need a write barrier because nobody's ever going to see that object. It lives on the stack. Now, the reason why we can't do stack allocation to stack allocation is exactly this case. Let's have this example here where we have 2 objects pointing to each other. Now we get to the bottom part, we load the original test object from the wrapper, we do t.x, everything's good, we remove the write barrier. Now what if there was another code in between like this? And this actually gave us a heap hoop. Now coming down here, it's either a heap or a stack object. Down this t1.x, so we don't know. In that case, two ways. We can actually detect this case with analysis and reject it, which would reject certain candidates, or we extend the right barrier to actually look at the stack range and say, yeah, this falls within the stack, you're good, keep going, don't worry about that. So it would increase the cost of the right barrier if we did that approach.
Very interesting results. Thanks a lot. Quick question. Have you considered allocating such objects on heap instead of on stack? But just
Nope.
like...
No, you mean reserve a special heap region for these
Like
kind of objects?
with T-labs. You would allocate T-labs, but just for duration
Of the stack.
of a single call, or just chunk them. And by that, you can significantly simplify the requirements to the runtime. You don't need to treat special objects on the stack, since everything stays on heap.
Well, I have to consider how that would work. I can't think off the top of my head, but yeah, we'll think about it. Maybe there's a way that we actually can do that. We didn't consider it, no. I think there was a question here.
Just looking forward to
The
try
path.
it out the path when it comes
Yeah.
out, because in the memory API that I showed before, we had some benchmarks that are very problematic and stress the flow-sensitive case that you were mentioning before.
Yeah, especially with the immutable
Yeah.
trend, and I love immutable objects myself. It actually creates copies every time, which we're hoping that this would actually take care of.
Charlie.
So I just want to be clear that there's still a limitation that there's no partial escape analysis here. There's no lazily standing stuff back up. Okay.
Yeah, absolutely. So we can look into that next. I mean, right now we're not doing it. So anytime we see something that escapes, for us escapes. It doesn't matter if it's a cold call or something that's never reached. We're just, okay.
Okay, well, I think we're done. Thank you.
Thanks. Thanks again, everyone.